What if you could turn a regular school field trip into a real scientific expedition? Well, today, that's exactly what we're going to do. We're heading out to Scotland's River Carron to tackle a really big question. How does a river actually change as it makes its way from the mountains all the way down to the sea?
And look, to find those answers, you really got to get your feet wet, right? This isn't something you can do just by looking at maps from a distance. Nope. It's all about getting in the river, taking measurements, and just letting the water and the stones tell you their story. This is what science in action looks like.
Okay, so every good expedition needs a plan, kind of like a mission briefing. For us, that means we've got to understand the theory before our boots even touch the water. We need to know what we're looking for out there. And this is basically our treasure map. It's called the Bradshaw model, and it's a theory that pretty much predicts how a river should change. So as we travel downstream, it says something should get bigger. The river's width, its depth, its speed. But at the same time, other things are supposed to get smaller, like the size of the stones on the riverbed and how steep the slope is. So yeah, this model, it's going to be our guide.
Now, a model is one thing, but to actually test it, we need to ask some really specific, measurable questions. In science, we call them hypotheses. So this is the part where we gear up and figure out our exact mission objectives.
All right, so here are the 5 big questions we're setting out to answer. They're all based on our map, the Bradshaw model. Will the river get wider, deeper? Will the stones get smaller and rounder? And finally, will the water actually flow faster? To find all that out, we're going to need the right tools for the job.
For instance, to see if the stones are getting smaller, you can't just eyeball it. You have to be systematic. So we'll pick up stones and measure what's called the B-axis. That's not the longest part, not the shortest, but the one right in the middle. And a simple little tool called a caliper gives us a precise number every single time. It's all very methodical, and that's what makes it accurate.
So how in the world do you measure the steepness of a river? Well, it turns out you just need 2 poles and this cool tool, a clinometer. You just sight from the same height on both poles over a certain distance, and bam, you can measure the angle of the slope, just like that. It's classic, hands-on geography, and it's actually pretty cool.
All right, we've got our theory, we've got our questions, and we've got our tools. It is time to begin the expedition. And check this out. For our visual logbook, we're going to be using these incredible field sketches that were drawn by the students themselves. How cool is that?
Okay, here we are. Site 1, way up in the Campsie Hills, right near the river's source. And this sketch just captures it perfectly, doesn't it? You can see the wild vegetation, the forestry on the hills, and a river that's still really narrow and shallow, just full of these big, chunky stones. This is pretty much the river in its youth.
Now we're moving downstream to Site 2, and wow, the change is already so obvious. You can see in the sketch the river is getting wider, it's getting deeper, and you also start to see human influence here with those reservoir walls. The notes even mention that the stones are starting to smooth out. They're becoming less angular. Interesting. And here we are, our final stop, Site 3. The transformation is just dramatic. The river is now, and I'm quoting the notes here, much wider and a lot deeper. And the whole landscape has changed too. You see housing, businesses, footpaths. The notes confirm it. The sediment is definitely smaller and rounder. So we've seen the change with our own eyes, but now we need to see what the data says.
This is the moment every scientist waits for, right? The aha moment. We've collected all our data, and now we get to process it and see if our observations out in the field actually match reality. So does the evidence support the Bradshaw model? Let's find out.
So let's start with our first big test. The model predicts a wider and deeper river, right? Which means it should have a larger cross-sectional area. It also says the flow should get faster. So the big question is, did our measurements on the River Carron actually confirm this? And the answer is a big, resounding yes. I mean, look at this. The cross-sectional area, which is just the width times the average depth, it grew from just 0.2 square meters at our first site all the way to 1.8 by our last one. That is a 9-fold increase. The data here is crystal clear. Okay, what about speed? Now, you might think a tumbling mountain stream would be faster, but actually, downstream there's less friction with the riverbed and the banks. And sure enough, the data confirms it. The velocity nearly doubled, going from 0.28 meters per second up near the source to over half a meter per second at Site 3. Boom. 2 hypotheses confirmed.
All right, next up. What about the stones? What happened to all the rocks and pebbles that the river is carrying along?
what geographers call its load. Did our fieldwork show that they really do get broken down and smoothed out along the journey?
Oh, absolutely. The proof is right here in the numbers. The average stone size back at Site 1 was almost 11 centimeters. By the time we got to Site 3, it had shrunk all the way down to less than 4. That just shows you how incredibly effective the river is at breaking down its load over distance.
And just look at the change in shape. At Site 1, you see a real mix of stones, and a lot of them are sharp, really angular. But by Site 3, poof. Those have almost completely vanished. They've been replaced by much, much rounder stones. It's like the river is acting like a giant natural rock tumbler.
So, the data is great. It tells us what happened. But the real science, the fun part, is explaining why it happened. So let's connect the dots and tell the full story of our river, looking at the actual processes that are shaping it. First off, why did the river get wider and deeper? Well, there are two main reasons. First, you've got hydraulic action. That's just the sheer force of the water blasting away at the banks. And then there's abrasion. This is where the river uses all that sediment it's carrying, the sand, the gravel, the stones, almost like sandpaper, just grinding away at its own channel.
And the stones? Why do they get smaller and rounder? Well, that's a process called attrition. It's pretty simple, really. As the river carries all those rocks, they're constantly bumping and grinding against each other. It's like a demolition derby in there. This constant crashing breaks off the sharp edges and smashes bigger rocks into smaller ones. And that's exactly how you get those smooth, rounded pebbles we found at Site 3.
But you know, there's more to the story. A river isn't some closed system all on its own. As it flows, other smaller rivers, we call them tributaries, they join in. And all that extra water means more volume and way more energy. A more powerful river can, you guessed it, erode more, transport more sediment, and overcome friction way more easily. And that helps explain that surprising increase in speed we saw earlier.
So, all in all, our expedition was a huge success. We set out to test a model, and our fieldwork on the River Karen, it confirmed it perfectly. The story the data told us was exactly what the Bradshaw model predicted it would be. The river becomes wider, deeper, and faster, and the stones become smaller, rounder, and smoother. The river just systematically transforms itself and the landscape around it.
But our journey also showed us something else, clear human influence, like the Karen Reservoir. We've just seen the story that a natural river tells, so that leaves us with one final, really important question to think about. How do our actions, things like building massive dams, interrupt that natural story and completely change a river's future?